Imagine a colossal red lantern breathing in deep space, its slow exhalations painting drifting veils of dust that glow like midnight snow. This is VY Canis Majoris, the red hypergiant rewriting its own sky. Tonight sink into a calm journey through eruptive plumes, shimmering arcs, and the quiet engines that move them from warm inner light to the cool edges where future worlds begin. If this gentle voyage into cosmic weather soothes your mind, please, like the video, subscribe for more sleep-friendly science, and share your favorite moment in the comments to keep the starlight flowing. To begin, a slow red ember rests within the constellation of the Greater Dog, and it glows through its own weather like a lantern behind gentle fog. VY Canis Majoris is a red hypergiant star in the constellation Canis Major, and high-resolution imaging reveals asymmetric plumes of dust that rise and drift away from its surface. This matters because the way such a massive star sheds matter sets the terms for its remaining life, and for the dust that later becomes part of planets and clouds between stars. By the end, the identity of this star, its place, and the outline of its unusual surroundings become clear enough to hold calmly in mind. A red hypergiant is an extremely luminous, swollen, cool supergiant star, and VY Canis Majoris stands among the largest known. The star sits thousands of light-years away, far enough that its surrounding material looks like a soft haze from a distance, yet close enough that modern observatories trace the shape of that haze. Mass loss means matter flowing away into space as wind or bursts, and in this case the flow is not uniform. It appears in clumps, arcs, and fans, as if breaths of warm air have cooled into visible drifting snow. The picture that astronomers assemble comes from many kinds of visible light that sketches scattered grains, warm infrared light that sees heat from dust, and radio waves that track gas molecules as they move. The Hubble Space Telescope maps knots and filaments that spread unevenly. The Very Large Telescope resolves bright patches that hint at giant cells on the surface. The Atacama Large Millimeter Array measures the motion of gas in the surrounding envelope, and the James Webb Space Telescope adds a deeper view into cooler dust farther out. Each instrument contributes a layer, and together the layers form a nested portrait close to the star are turbulent flickers. Farther out lies a slow, turning halo of dust like breath in cold air. Beyond that, arcs peel away as the memory of earlier events. Evidence suggests that large convection cells stir the surface. Convection cells are hot rising bubbles and cool sinking lanes, and on a star this large, each cell can span a vast fraction of the visible disk. Where a cell rises, shocks can form, and shocks push material outward until it cools enough for solids to condense. Circumstellar means surrounding the star, and in this circumstellar zone the first grains of dust appear, likely minerals like silicates that grow as they drift. That growth matters because the grains couple to light. Starlight pushes on them, and they push on gas, and the wind strengthens. The result is an outflow both steady and punctuated, steady in its overall drift, yet punctuated by plume events that leave imprints at odd angles. A small payoff arrives here. The odd leaning shapes are not random decoration, but records of launch sites on the surface where energy once rose strong enough to lift matter high. The light from the star varies slowly with semi-regular patterns that suggest deep motions and surface changes, and these slow rhythms line up with the idea that waves and cells help prepare each ejection. Variability means the brightness changes with time, sometimes in long, rolling cycles, and sometimes with shorter ripples, and these patterns offer quiet clues without demanding precise numbers. Distances and sizes carry uncertainties, and this is handled gently. The star is extraordinarily large even within broad ranges, and the uncertainty does not disturb the main picture of a heavy cooling atmosphere that lets dust be born nearby. The star exists now in a late phase of massive star evolution, where mass loss dominates the story, and this late phase is not an alarm but a process that feeds the interstellar medium with fresh solids. Interstellar medium means the gas and dust between stars and the dust from VY Canis Majoris will one day be part of future clouds that make new stars and planets. A visual anchor helps imagine a slow snowfall under an orange street lamp where the flakes drift sideways along quiet lanes of air. The plumes of VY Canis Majoris look like that, except the lamp is a star and the lanes are guided by heat and gravity. The immediate environment is not a neat sphere but an asymmetric collage, and that asymmetry matters because it hints at steering influences like rotation and magnetic fields that may tilt or thread the flow. Rotation does not need to be fast to leave a mark on such a broad atmosphere, and magnetic fields, even if modest, can shape paths for charged particles and indirectly for dust formation zones. Another small payoff follows. By looking at the motion of individual clumps, astronomers can read their ages like dates on tree rings, recovering a timeline of recent ejections. This timeline suggests that the star does not simply blow evenly, but instead sighs in episodes, each episode sending out a structured plume that later becomes an arc far away. The big takeaway for this opening is simple. VY Canis Majoris is a red hypergiant that constantly remakes its own sky, building an uneven shell of dust and gas that stores the memory of its inner weather. The story matters because it shows how the most massive stars return material to space, and because it offers a real nearby example that grounds models of stellar life cycles. The promise continues softly. Next comes a steadier sense of size and power, and then a calm walk through the plumes themselves, their chemistry, their motion, and the forces that guide them, so that the strange beauty of this star becomes clear and restful, rather than distant and overwhelming. To continue scale and glow settle into view as if a dim room slowly brightens, and the star takes a shape that can be calmly held. The early takeaway is simple for VY Canis Majoris size, and brightness act as anchors for understanding rather than precise targets, and these anchors explain why matter lifts from the surface and drifts into space. Luminosity means total light energy released by a star, and the luminosity of this red hypergiant is extraordinarily high for a cool star. Cool here means a lower surface temperature than white or blue stars, so the light leans toward red and infrared bands where dust can absorb it gently. Radiation pressure means pressure from light pushing on matter, and in a hypergiant that pressure becomes a patient wind. A visual anchor helps a wide sail under a constant breeze pressed smooth without strain. The dust around VY Canis Majoris feels a similar continual push. Brightness alone does not tell the whole story because the star is large beyond everyday sense. The photosphere means the visible surface, and for this star that surface would engulf the inner planets and reach toward the orbit of Jupiter. An astronomical unit means the average distance between Earth and Sun, and the radius measured in those units is so great that the mind must switch to pictures rather than counts. This scale matters because a larger surface offers more places for plumes to rise, and a greater light output supplies the steady push that keeps them moving. Uncertainty enters gently because dust obscures and distorts the view. Extinction means dimming by dust and gas, and within the envelope of VY Canis Majoris extinction changes with direction, so some lines of sight appear darker while others open like thin fog. The uneven screen does not undo the picture. It simply reminds that measured sizes and brightnesses carry ranges. The payoff is that even the smallest reasonable estimates still imply an extraordinary star, and the largest do not break the story either. Close-in gas cools until seed clusters form. Then silicate minerals grow and turn into dust able to feel the wind of light. Here the numbers fold into a simple image, a flickering furnace behind veils, where grains begin to crystallize and then slide outward along gentle lanes. Because the star is enormous, gravity at the extended surface is softer than for a compact star with similar mass, and that softness helps matter escape once light gains a grip on grains. A small payoff settles in high luminosity broad surface, and cool layers combine into a natural recipe for outflow without violence. The brightness that leaves the star also returns as warmth when dust absorbs it and re-radiates it. That is why infrared views show a steady glow that outlines arcs and fans rather than a blank space. Because scale is so large, the language of distances must stretch. The condensation zone where dust first survives is not far from the photosphere in relative terms, but because the star is huge, that near region still occupies a space larger than the inner parts of typical planetary systems. This is why a plume can retain its identity for a long time as it travels outward. The journey from near to far is measured not in quick steps but in seasons of motion. Brightness also carries hidden complexity, because the envelope scatters light. Scattering means light is redirected by particles, and in the cloud around this star some brightness does not come directly from the photosphere, but from light bounced off dust like sunlight off high clouds. This means that brightness at different bands must be interpreted with care, but the ranges do not disturb the central idea. The central idea remains that a star of enormous radius, gentle surface temperature, and very high luminosity naturally produces dust close in and pushes it outward with patience. A further payoff rests here. Knowing the approximate size and light output allows a rough estimate of how long it takes a plume to become an arc at a given distance, which ties motion to memory. The picture would be incomplete without noting how the scale determines visibility. Invisible light, thinner dust allows brief glimpses toward the inner envelope, while thicker regions act like frosted glass that smears detail but preserves glow. The term outflow simply means material leaving the star, and for VY Canis Majoris that outflow is not a smooth shell but a set of favoured lanes that widen with distance. Another visual anchor can stand here. A slow snowfall under a street lamp does not make a uniform fog. It makes bright streaks where air guides flakes and softer gaps between streaks where the wind is still. In the same way, scale and light together select paths through which dust finds its way outward. The final reassurance for this section is that exact values are not required to understand the behaviour. Whether the true radius sits toward the lower end of estimates or toward the higher, whether the exact luminosity leans one way or another, the essential pattern holds a gigantic radiant surface, breathing a patient wind that carries dust into a clumpy illuminated envelope. This understanding calms the mind because it shows a system following steady rules with differences of detail, shading the view but not overturning it. And as the measure of size and brightness settles, a natural next step appears distance, because distance ties brightness to power with a firm knot, and setting that knot will steady every number that follows, smoothing the path into the following section. To continue distance is the quiet foundation under every number, like a steady floor beneath a dim room, and the early takeaway is that a good distance range turns confusion into calm, because size, brightness, and motion all rest on that single measure. Distance ties observed light to true power because light spreads out through space. Double the distance and brightness falls by 4, and that square relationship means even a modest error can ripple through every estimate. Parallax offers the most direct path. Parallax is the apparent shift of a nearby object against a distant background as Earth circles the Sun. For a compact star with a clean point-like image, parallax is straightforward, but VY Canis Majoris wears an uneven cloak of dust that scatters light and moves the center of brightness around. This shifting center makes the tiny annual wiggle harder to read in visible light, so the usual method must be framed gently and checked against other approaches. Radio observations open a clearer window. Mesa emission is naturally amplified microwave light from specific molecules in gas, often water or silicon monoxide, and Mesa spots act like bright tiny beacons embedded in the outflow. Very long baseline. Interferometry is a technique that links radio telescopes across continents to behave like one giant dish, and it measures positions so precisely that the small yearly shift of the Mesa spots can be traced even when dust blocks visible light. Because the Mesas belong to the envelope of VY Canis Majoris, they move with it, and their parallax gives a geometric distance that does not require a standard candle or a model atmosphere. A small payoff lands here when Mesa parallax and careful visible light measurements point to the same general range. Confidence rises even if exact values differ by a little. There is also the temptation to use spectral type and brightness relations, sometimes called spectroscopic parallax, but that approach rests on families of stars that do not share the unique traits of a red hypergiant with heavy mass loss, so it must be handled with caution. Kinematic distance methods turn measured speeds into distances by comparing to models of how gas circulates around the galaxy. But local motions near such a massive star can be unusual, and dust lanes along the line of sight can bend that logic. These methods can guide but should not dominate. The European Space Agency Gaia mission measures parallaxes in visible light with remarkable reach, yet extended nebulosity and slow brightness. Changes can bias solutions for very unusual stars like this one. So Gaia values for VY Canis Majoris are signposts to be read alongside radio results, rather than treated as the only truth. Extinction is the dimming caused by dust and gas. Reddening is the shift of colour toward red when dust scatters blue light away. Extinction and reddening vary around the star, which means the same object can appear slightly different depending on viewing direction, and that unevenness adds a gentle layer of uncertainty that we accept without anxiety. When the different strands are braided together, a stable picture appears. VY Canis Majoris lies at a distance of a few thousand light-years, close enough for modern instruments to resolve its environment, yet far enough that all measurements must respect subtle biases from dust and asymmetry. The exact figure is often discussed, but the important point for this story is that the range is narrow enough to steady the narrative. A visual anchor helps imagine standing on a pier at night, measuring the distance to a lantern through drifting fog by taking small side steps, and watching how the lantern seems to shift against distant stars. The parallax is that side step, the fog is the dust. Envelope, and the distant stars are the fixed background. Why this matters becomes clear in practical terms. Luminosity scales with the square of the distance, so a firm range locks the star's true power into a healthy bracket. Radius scales roughly with the measured angular size times the distance, so a better distance turns a disk on the sky into a real size that the mind can picture. Mass loss rate depends on both the amount of material measured and the space it fills. With distance in hand, the flow can be converted from a pattern of light into a rate that can be compared with other massive stars. The motions of clumps turn into reliable ages when angular speeds become physical speeds through multiplication by distance, and that conversion builds a gentle timeline of past ejections. Here a small payoff settles in, even if one study leans toward a slightly closer value and another leans toward a slightly farther value. Both agree that the star is luminous enough and large enough to forge dust close to its surface, and to drive a patient wind that builds plumes into arcs. Another visual anchor can rest. Here think of beads sliding outward along quiet strings. Knowing the spacing of the strings gives the scale of the whole necklace, and distance plays that quiet role for the envelope of VY Canis Majoris. The path to distance also teaches how to observe the star wisely. Invisible light scattered photons can shift the center, so astronomers weigh images over time rather than seize on a single snapshot. In radio light, mesospots move both because of the parallax and because of the flow itself. So long timelines let the parallax signal wriggle free from the steady drift. In the infrared thermal glow maps where dust stores the star's energy, and that map makes it easier to choose where to focus parallax attempts and where to be cautious. The soft conclusion for this section is that distance for VY Canis Majoris is not a sharp single value, but a well-held band that steadies all other ideas. With that band in place, each later estimate stays consistent and reassuring, and the story can proceed without fear that a new measurement will overturn the scene. The natural next step is to listen to the star's light itself and trace its slow patterns, because those faint rhythms set against a known distance will link surface changes to the outward breath that becomes the plumes described ahead. To continue, the star's light breathes in gentle patterns that rise and fall like a resting tide, and the early takeaway is that small changes in brightness carry quiet messages from the surface and from the layers just beneath. Semi-regular variability means brightness that drifts up and down with loose cycles rather than a strict schedule, and that looseness matters because it points to living processes such as giant surface cells, slow waves, and cooling and warming patches that come and go. Photometry is the measurement of a star's brightness with time, and the long record for VY Canis Majoris shows slow undulations with hints of nested rhythms, some lasting many months, and others shorter, all moving without hurry. A small payoff arrives here when the star grows a little brighter, in red and infrared light, while staying muted in visible light. It suggests that dust nearby has shifted slightly or warmed, not that the core has changed sharply, and that distinction calms the picture by keeping the changes at the surface and in the envelope. Pulsation in this context means the star's outer layers expand and contract, and even shallow pulsations can alter temperature and pressure, enough to nudge dust formation zones outward or inward by a small amount. Convection cells are rising and sinking regions that carry heat, and on a hypergiant each cell may span a large fraction of the visible disk, so when one cell strengthens it can lift gas higher and make a local bright patch that later fades as the gas cools. The light curve is a plot of brightness over time, and in this star the light curve resembles a slow rolling landscape, with soft hills rather than sharp peaks, which hints that multiple processes overlap to make the observed pattern. Another small payoff settles in the timescales of these hills match the timescales needed for gas near the surface to move cool and condense into the first grains, so brightness changes and dust events can be linked without strain. Polarization is light, whose waves prefer one direction, and dust grains can polarize scattered light, so small swings in polarization that track brightness reinforce the idea that changes in the nearby envelope are part of the rhythm. Spectroscopy is the spreading of starlight into colors to read the fingerprints of atoms and molecules, and shallow shifts in molecular bands over time suggest temperature changes in the outer layers where those molecules form. Doppler shift is the change in wavelength caused by motion toward or away from the observer, and tiny shifts recorded across repeated observations reveal that parts of the atmosphere drift outward or inward, in step with the light variations further tying brightness to breathing motions. A visual anchor helps imagine the glow of a paper lantern seen through a thin veil, where faint ripples in the veil slide slowly, and the lantern's light seems to deepen and soften in turn. The star's light behaves like that, rising and easing as the veil and the warm air move together. The why of this section rests on insight. Faint rhythms allow astronomers to connect surface physics to the outflow pattern, and that link matters because it helps explain why plume events happen at certain times and not at random. When the star expands a little, the surface cools a little, and cooler layers allow more molecules to form. Molecule formation improves the ability of gas to condense dust once it is pushed outward, so a gentle brightening followed by a soft dimming can be the signature of a cycle that prepares a plume. This process is not a metronome but a set of overlapping beats. One beat may come from a large convection cell rising and then fading. Another may come from a global standing wave that shifts the mean pressure. A third may come from a slight change in how much dust the outflow carries along the favoured lanes. The payoff is that no single mechanism needs to do everything. Instead, the light records a blend, and the blend still points to a patient engine for mass loss. Scattering plays a role in shaping what observers see. Scattering is the redirection of light by particles, and an asymmetric envelope means that some lines of sight brighten when a plume drifts into a position where it scatters more starlight toward the observer, while other lines of sight fade when a plume thickens and hides the inner glow. This subtle dance can produce short ripples on top of longer waves, and careful observers use many wavelengths together to separate intrinsic stellar changes from envelope geometry. The rhythm also provides a clock for planning observations. When brightness trends upward at longer wavelengths, infrared cameras can probe the warm dust closest to the star, while spectrographs can watch molecular features that react quickly to temperature shifts. When brightness trends downward after a mild expansion, imaging polarimeters can measure any increase in scattered light that hints at new grains forming and drifting outward. A second visual anchor can rest. Here think of a lake at dusk where breath-like breezes trace soft patterns that repeat but never exactly, and where the reflections of distant lamps wax and wane as ripples pass. The star's light carries that same mood of familiar change without sharp edges. The faint rhythms also set boundaries on more dramatic interpretations. A large, sudden drop in brightness could suggest a violent event, but in VY Canis Majoris the record more often shows gradual shifts that align with cooling patches and plume drift, and this steadiness supports the broader theme that outflow is generally patient with occasional accented notes rather than crashes. That steadiness matters for understanding the later stages of massive star evolution, because it implies that a significant fraction of mass loss can occur through repeated moderately strong episodes, rather than only through rare extremes, and that view connects gently to the observed arcs and knots that fill the envelope. A small payoff returns by cross-matching the phases of light change with the proper motions of clumps measured over the years. Researchers build a timeline where certain brightenings precede the launch of material seen later, as a distinct feature turning light into a guide for reading the nebula's history. The lesson of this section is therefore simple and restful. Brightness changes in VY Canis Majoris arise from a mix of breathing layers, surface cells, and moving dust. These changes are slow and semi-regular, and they create a soft metrical background upon which eruptive plumes can be set. The rhythms are not a warning, but a language that the star speaks as it sheds mass and cools the immediate sky. With the calm pattern of light understood, the path forward is clear and gentle step from the language of brightness into the shapes themselves, where eruptive dust plumes unfurl like long quiet banners and watch how those banners take form, thicken, and drift into the clumpy environment that surrounds the star. To continue, eruptive dust plumes rise from the vast surface like slow banners catching a steady breeze, and the early takeaway is that these plumes are not merely decorations, but the main channels by which the star sheds mass and writes its recent history into space. A plume is a focused stream of gas and dust that leaves a source region with a preferred direction, and in VY Canis Majoris the plumes appear at odd angles, as if a lantern were exhaling along tilted chimneys. Episodic mass loss means matter leaves in bursts separated by quieter intervals, and those bursts matter because they create clumps and fans that later appear as arcs farther out. Observers see these structures with instruments that work in different kinds of light. The Hubble Space Telescope shows scattered light from dust grains that sit closer to the star than one might expect. For a hypergiant, the Very Large Telescope resolves bright knots that mark where a plume once left the Atacama Large Millimeter Array, traces molecules flowing through the envelope and records their speed, and the James Webb Space Telescope outlines cool, extended dust that keeps the memory of earlier ejections. A small payoff arrives here taken together. These views reveal that the star does not blow a smooth shell, but prefers discrete launch sites whose directions repeat for a time, implying that the forces under the surface hold patterns long enough to shape the environment. The physics that gives a plume its first push can be described gently. A giant convection cell lifts hot gas upward. A shock is a sharp change in pressure moving through gas, and shocks arise where rising material meets slower layers. When gas passes through a shock, it can expand and cooling allows molecules to form. Condensation in this context means atoms and molecules sticking together into solid grains, and grains are essential because light pushes grains more effectively than it pushes bare gas. Once grains appear, radiation pressure begins to matter. Radiation pressure is the push from starlight, and near a luminous red hypergiant that pushes steady and patient more like a constant tide than a gust. The grains share momentum with surrounding gas, and the combined flow becomes a wind that thickens into a plume wherever the initial lift was strongest. A visual anchor helps imagine warm breath in winter air, where exhaled vapor curls into a pale streamer that leans with the breeze. The plume behaves like that, except the breeze is light itself, and the streamer is made of mineral grains. Another payoff settles in because the star is cool at the surface. The condensation zone sits relatively close, and this gentle proximity means that small changes in temperature or pressure can toggle dust formation on or off above a specific patch, which explains why plumes appear and fade irregularly. The envelope is asymmetric because plumes are not evenly spaced, and because each plume follows its own lane that widens with distance. Optical depth is a measure of how much light is blocked along a path, and optical depth changes from direction to direction as plumes drift and thicken, so the view toward the star can brighten or dim even if the star's core output remains steady. Scattering is the redirection of light by particles, and scattering off plume dust brightens certain angles the way high clouds can make halos around a lamp. Polarimetry is the measurement of the preferred direction in light waves, and imaging polarimetry uses that property to separate scattered light from direct light producing maps that trace the content and shape of the plumes with a clarity that simple brightness images cannot provide. Interferometry links telescopes to achieve sharper resolution, and interferometric imaging of near-infrared light reveals patchy structures just above the visible surface which align with the footprint of later plumes. A small payoff follows by comparing the position angles of surface patches with the later arcs seen farther out, observers match birthplaces to descendants, and so turn morphology into a timeline. Chemistry adds a calm layer. Spectra of the gas show molecules such as water and silicon monoxide, and these molecules survive only in specific temperature and density ranges. Where a plume begins, the gas density is higher, the temperature cools past key thresholds, and silicate grains begin to grow. Silicates are minerals built from silicon and oxygen, often carrying magnesium or iron, and in these environments the precise mix may vary with distance from the star. Albedo is the fraction of light reflected by a surface and dust. With moderate albedo both scatters and absorbs, which means it glows in infrared light, while also sending some starlight sideways toward the observer. The combined behavior explains why a plume can look bright in scattered visible light when near the star, yet glow softly in infrared light when it has travelled outward and cooled. A second visual anchor can rest here. Think of sparks from a bonfire that drift up, fade from bright orange to deep red, and then become dark grains that ride the air. The plume carries the same slow change from near-reflective glitter to far warm embers. The role of geometry is gentle but decisive. A favoured direction may come from a long-lived convection cell from a magnetic loop that arches above the surface, or from a slight rotational tilt that makes certain latitudes more welcoming to outflow. Rotation does not need to be fast to matter. On a vast star, even slow spin stretches the atmosphere into a shape where pressure and temperature vary with latitude, and that variation can steer plumes like grooves guide a wheel. Magnetic fields can channel charged particles, and by altering the flow of those particles, the fields can change how and where molecules form, subtly sculpting condensation zones into lanes and arcs. Because the guiding forces change slowly, several plumes can launch from a similar region over the course of years, layering their paths into a fan that opens like a hand. The payoff is a calm understanding. Asymmetry is not chaos but memory. The memory of where the surface once lifted and how the overlying layers allowed that lift to become a wind. Reading motion turns the picture from static to living. Proper motion is the change in position on the sky with time, and when astronomers track bright knots across repeated images, they see the knots drift outward with speeds that are modest by stellar standards, fast enough to carry a clump across the inner envelope within a handful of years, but slow enough to preserve structure for a long while. When those speeds are combined with distance, each knot becomes a clock that points back to a launch date. In this way, the map of plumes is also a calendar of events, a gentle archive written in arcs and fans. The soft close of this section arrives with a practical point that reassures. Eruptive dust plumes explain both the brightness fluctuations and the asymmetric halo, and they provide the channels that feed the larger nebula with material. The star is not exploding. It is breathing in structured episodes that add up to a life shaped by patient release. With plumes understood as the handwriting of the surface, the narrative can move outward to the larger canvas they create into the arcs, knots and layered geometry of the surrounding nebula, where direction, age and composition come together into a clear three-dimensional sketch. To continue, the surrounding nebula of VY Canis Majoris appears as a clumpy garden of arcs, knots, and faint fans that cross and overlap like leaves pressed into a slow-moving stream, and the early takeaway is that geometry preserves memory. Each bend and bead records a past ejection, and together they form a three-dimensional diary of how the star breathes. A nebula is a cloud of gas and dust, and in this case it is the immediate envelope that the star has built from its own outflow, shaped not into a tidy sphere, but into an uneven collage whose asymmetry matters because it reveals the forces that steer mass into space. The first gentle truth is that arcs do not lie at random. Many gather into partial rings that open in certain directions as if a slow hand had fanned pages from a single hinge, which hints that favoured launch sites on the surface have persisted long enough to layer their traces. Knots are compact clumps within the arcs, and their brightness against surrounding glow means that local density and grain growth are higher there. So the knots act both as signposts and as weights that carry momentum outward. A visual anchor helps imagine a lantern wrapped in drifting veils, where occasional folds catch the light and define curved edges. The nebula looks like that, with folds that mark where past plumes spread and cooled. Mapping such structure begins with careful imaging in different colours and with measurements of polarization that separates scattered light from direct light. Polarimetry is the measurement of the preferred direction of light waves after scattering, and image in polarimetry turns that preference into a map that outlines dust lanes and the curvature of arcs since scattered light is strongest at certain angles. Spectroscopy. The spreading of light into its colours adds a second layer because it shows which molecules inhabit which lanes and how their signatures change with distance. Interferometry. The linking of multiple telescopes to create a sharper view resolves the region just above the visible surface where the flow begins, while wide-field infrared images show where arcs from older events lie like rings on calm water. Deprojection is the process of turning a flat sky picture into a three-dimensional estimate by combining geometry with motion, and in the nebula around VY Canis Majoris, deprojection uses proper motions and the brightness patterns of scattered light to infer which features sit in front, which behind, and which lie near the plane of the sky. A small payoff arrives here. Several broad fans appear to lean in consistent directions, suggesting that the star favoured certain latitudes for ejection, over spans of years turning the envelope into a set of overlapping lobes rather than a uniform shell. Optical depth is a measure of how much light is blocked along a path, and optical depth in this envelope varies with direction, because dust density and grain size vary from plume to plume. High optical depth hides the inner regions and leaves only a soft outline, while moderate optical depth brightens edges through forward, scattering the way thin clouds enhance a halo around a lamp. Shadowing also matters. When a recent plume thickens close to the star, it can cast a radial shadow into the outer envelope, so that more distant arcs show dim wedges that align with that inner lane. These shadow cones are gentle guides to depth ordering and confirm that the nebula is layered like a stack of shells whose rims are incomplete. A visual anchor can rest here. Think of sunlight entering a forest canopy and creating shafts that leave dim lanes on the ground. The nebula's arcs and shadows create the same quiet geometry in space. Motion turns these shapes into clocks. Proper motion is the change in position on the sky with time, and by tracking knots over many years, observers find outward drift that is steady enough to treat as nearly uniform, within each feature a pattern known as homologous expansion. When combined with distance, the proper motion yields a physical speed. Then dividing the separation from the star by that speed gives an ejection age. Arcs with similar ages but different directions imply a burst that vented along several nearby lanes at once, while arcs of different ages that share an alignment imply a long-lived launch region. The payoff is a simple calendar. Inner arcs are young and trace recent surface activity. Middle arcs are older and record earlier episodes. Outer arcs are older still and preserve the memory of a time when different lanes were favoured. Composition and temperature add quiet colour to the sketch. The envelope is oxygen-rich, so molecules such as water and carbon monoxide are abundant, and their strengths in spectra decline with distance as gas thins and cools. Dust temperatures fall as grains drift away from the star's light, so infrared color maps paint the inner arcs warmer and the outer arcs cooler, a gradient that reassures because it matches expectation. Grain size matters because small grains scatter light more efficiently at short wavelengths, making blue and visual images emphasize fine structure, while larger grains radiate more strongly in the infrared, making long wavelength maps emphasize smoother bodies and thicker lanes. Polarization patterns reveal grain alignment trends and confirm that some arcs are inclined surfaces rather than flat rings, tilting toward or away from the observer. Inclination is the tilt of a structure relative to the line of sight, and mild inclinations across multiple arcs suggest that the envelope is not strongly bipolar, but exhibits a set of lobes and fans of varying openness, with hints of an equatorial preference that is gentle rather than strict. Rotation can contribute to such an equatorial tilt by lowering effective gravity near the equator of the swollen star, and even slow rotation on such a vast body can nudge pressure and temperature patterns to favor certain latitudes. Magnetic fields, if present, can guide the flow of charged particles and influence where molecules form and grains condense, leaving behind arcs that share a curvature consistent with looped field lines, though this picture remains a possibility rather than a demand. Another small payoff follows by comparing the position angles of arcs with the brightest surface patches seen in high resolution, near-infrared snapshots. The likely footprint of plume sources can be matched to their descendants, linking geometry across scales from the surface to the remote halo. Luminosity and geometry meet in the brightness of arcs. Arcs closer to the star receive stronger illumination and can appear brighter even if they contain less mass, while distant arcs can glow softly due to their greater volume despite lower illumination. To estimate mass, observers therefore combine scattered light images with thermal emission maps and with molecular line measurements that track gas directly, then use the distance and the geometry to turn brightness into density and volume. In this way, the nebula becomes not just a shape, but a budget that balances how much material left the star in each episode and where that material now resides. The gentle conclusion for this section is that the clumpy nebula of VY Canis Majoris is not chaos, but structure with memory written in arcs, knots, shadows, and fans that point back to favoured directions and to a patient sequence of ejections. This matters because a clear three-dimensional sketch constrains how mass loss proceeds in extreme late stages of massive stars and sets firm ground for models of how dust and gas return to the interstellar medium. With the geometry held calmly in mind, the path forward is natural step through the spectrum, and watch each kind of light reveal a different layer, so that the colours together bring the envelope into sharper and gentler focus. To continue, the star and its envelope reveal different moods in different kinds of light, and the early takeaway is that no single window tells the whole story. Optical light sketches edges infrared light, warms the interior submillimeter. Light weighs the cold body, and radiolight traces moving molecules with clocks built into their waves. In optical light, the envelope appears as a laced veil of arcs and knots, because small grains scatter short wavelengths efficiently, which sharpens filigree near the star and along the rims of plumes. Scattering is the redirection of light by particles, and the strength of scattering depends on grain size and viewing angle, so optical images emphasize fine structure and reveal the curvature of shells that would be blended together at longer wavelengths. The Hubble Space Telescope delivers this view with high contrast, and imaging polarimetry refines it by separating scattered light from any faint direct light that slips through thinner lanes. Polarimetry is the measurement of a preferred orientation of light waves, and the pattern of that preference maps the dust geometry, the way wind lines map ripples on a lake. A small payoff arrives here by reading the strength and angle of polarization across each arc. Observers infer which surfaces tilt toward the observer and which tilt away, turning flat shapes into gentle slopes carved by past plumes. Near-infrared light looks deeper because extinction is weaker at longer wavelengths. Extinction is the total dimming by dust and gas, and a lower extinction in the near-infrared allows telescopes to peer closer to the condensation zone, where solids first survive. The Very Large Telescope and the James Webb Space Telescope excel in this band, showing warm dust that still feels the full press of starlight and tracing lanes where new grains begin to push gas outward. Thermal emission is light released by warm matter, and warm grains glow in the near-infrared with temperatures that can be converted with simple models into distances from the star. Another small payoff follows. By measuring those temperatures across a fan, astronomers draw a temperature map that doubles as a distance map, identifying the birthplace of individual plumes and the gentle path they follow as they cool. Mid-infrared light carries the story farther out. Grains that have travelled beyond the most intense heat radiate more softly, turning bright knots into rounded clouds, and highlighting the bulk structure of fans and shells. The James Webb Space Telescope captures these regions with crisp sensitivity, revealing how separate plumes overlap and merge into broad lobes, and how shadow cones from newer, thicker lanes carve dim wedges through older dust farther away. A visual anchor helps think of a layered painting washed in red, gold, and ash, where close brush strokes show edges and distant washes reveal volume. The multi-wavelength portrait builds in that same layered way. Submillimeter light bridges the glow of dust and the voices of gas. In this band, the Atacama Large Millimeter Array is keenly sensitive to both faint continuum and to bright spectral lines. Continuum is broad, smooth emission, while a spectral line is emission at a specific color from a specific transition in atoms or molecules. Continuum maps the mass distribution of colder dust that no longer scatters much optical light, letting observers weigh the slow body of the nebula rather than only its shining rim. Spectral lines, especially from carbon monoxide, silicon monoxide, sulfur monoxide, and water, turn that mass into motion, because the Doppler shift converts line color shifts into speeds along the line of sight. The Doppler shift is the change in wavelength from motion toward or away, and when measured across many positions, it turns a still picture into a flow map. A small payoff lands here, combining proper motions seen in optical images with line-of-sight speeds from sub-millimeter spectra, yields full three-dimensional velocities for clumps which, when paired with distance, give precise ejection ages and a tidy calendar of episodes. Radiolight adds further clarity through maser spots that sparkle at very specific wavelengths from water and silicon monoxide. A maser is naturally amplified microwave emission, and maser spots act like bright beacons tied to dense pockets in the outflow. Very long baseline interferometry links radio antennas across the Earth to measure master positions and motions with exquisite precision, delivering geometry that resists the distortions of dust scattering. Radio measurements have another gift: they provide direct parallaxes where visible light would struggle, and those parallaxes ground the distance scale that supports every other measurement. The payoff is that the most delicate structures seen by the Hubble Space Telescope and the James Webb Space Telescope can be placed on a framework built by the Atacama Large Millimeter Array, and by radio arrays creating a nested portrait with reliable depth. Across all wavelengths, the same physical ideas knit the views together. Grain size evolves with time and distance. Small grains near the star scatter efficiently, larger grains farther out radiate strongly, and this size growth explains why optical images sparkle while infrared maps glow. Gas temperature and density set which molecules survive in which zones, so spectral fingerprints serve as gentle thermometers and barometers confirming that warm inner flows become cooler outer fans without surprise. Even uncertainties such as uneven extinction become manageable because multi-wavelength comparisons reveal and correct them. When an optical arc looks faint but a mid-infrared lane looks strong in the same direction, shadowing by a nearer plume is suspected not a true absence of material. A second visual anchor can rest here. Imagine a city seen at night through a gentle mist, where blue lights trace edges, amber lamps reveal streets, and long radio waves carry voices that say, "Who is moving where?" The nebula of VY Canis Majoris feels like that layered city in the sky. The why of this section is direct. Multi-wavelength vision matters because it links the launch physics near the star to the transport physics in the envelope, and then to the cooling and chemistry that decide what joins the wider interstellar medium. It matters because each band protects the narrative from bias. If one window blurs, another sharpens, and the combined image stays steady and restful. The soft close is therefore a promise of cohesion. With optical light tracing edges, with infrared light outlining warmth, with submillimeter light weighing cold dust, and with radio light timing the envelope becomes a well-held volume rather than a confusing fog. That volume begs the next question in the gentlest way. What engine under the surface prepares and launches these flows, and how do convection waves, rotation and magnetic guidance share the work of lifting matter into the lanes that the spectrum now reveals so clearly? To continue the engine that lifts matter from the swollen surface of VY Canis Majoris runs on patient overlapping processes rather than on a single dramatic switch, and the early takeaway is that convection waves shocks cooling radiation pressure on dust, slow rotation, and possibly magnetic guidance cooperate to turn inner heat into outward flow. Convection is the rise of hot gas and the sink of cool gas, and on a red hypergiant each cell can span a large fraction of the visible surface, so when a cell surges the overlying layers swell and thin like a slow tide. That swelling lowers the weight felt by gas near the top, and the reduced weight lets parcels climb higher before falling back, which primes them to cross into cooler zones where molecules can form. Waves add another gentle push. Acoustic waves are pressure waves that travel through gas, and gravity waves are buoyancy waves that ripple where light warm layers touch heavier cool layers. Both waves carry energy outward and can gather near the surface where their crests steepen into compressions. A shock is a sharp jump in pressure and temperature that forms when a wave crest steepens beyond a smooth ripple, and even a mild shock can jolt gas into a brief expansion that cools as it relaxes. Cooling invites chemistry. Molecule formation begins when temperatures fall enough for atoms to bond, and in oxygen-rich outflows molecules such as water and carbon monoxide appear, first setting the stage for solids to condense. Condensation is atoms and molecules sticking to form solid grains, and the first grains may be tiny silicate seeds that later grow as they drift. Here a small payoff lands the sequence of lift-shock cooling molecule formation and grain birth, naturally explains why dust appears close to the surface in specific lanes rather than everywhere at once. Radiation pressure then takes over. Radiation pressure is the push from starlight on matter, and grains feel this push strongly because their sizes match the wavelengths where the star emits most of its light. Grains share momentum with surrounding gas through collisions and through drag, and the mixture begins to flow outward along whichever direction the original lift favoured. Because the star is enormous, surface gravity is gentle, so even modest radiative pushes can win over time, and the outflow strengthens from a soft stir into a faithful breeze. A visual anchor helps picture a heavy curtain slowly billowing when a heater turns on in a quiet room. The rising stream begins at one spot, swells with warmth, and then the whole curtain eases outward. In the star, heat and light play those roles while grains and gas make the billowing body. Turbulence acts as the texture of this flow rather than as chaos. Turbulence is disordered motion that spreads energy across sizes, and in the rising lanes it mixes gas and seeds, thickening plumes and feeding them with fresh material until the growing grains pass a threshold where radiation pressure becomes the main guide. This layered handoff from lift to radiation is important because it yields a wind that is steady on average but modulated by eruptions whenever surface cells or waves align to give a localized boost. The next small payoff rests here. Sudden brightenings or dimmings seen at selected wavelengths align with this modulated engine, since new grains near the star scatter more light, while older grains farther out glow in infrared light, making the rhythm of formation and drift visible across the spectrum. Slow rotation of the star shapes this engine without needing to dominate it. Rotation spreads gravity slightly thinner near the equator and slightly stronger near the poles, and on a body this large, even a mild difference can tilt where pressure and temperature balance, making some latitudes friendlier to launch. Rotational shear is the change of rotation with latitude or depth, and shear can stretch convection cells and guide waves into lanes which later appear as preferred directions for plumes. The star's broad atmosphere likely hosts a tapestry of cells that live for months to years, with repeated surges from the same neighborhoods. This persistence explains why plumes can share alignments across multiple episodes, building fans that look like opened hands. A second visual anchor can settle here. Imagine a slow simmering pot, where large lazy bubbles rise in nearly the same places for a while, tilting as the pot is turned ever so slightly. The star's cells and gentle spin produce that same pattern of favoured launch points. Magnetic fields may add subtle guidance. A magnetic field is a region where moving charges feel a force, and magnetic field lines are paths that show field direction. Even modest fields can funnel charged particles and suppress turbulence along certain directions, creating pathways where molecules survive longer and grains assemble more easily. Magnetic waves travelling along field lines can also carry energy upward without much heating, until they dissipate near the surface where they stir gas and help launch material. The evidence for magnetic influence is cautious, drawn from polarization signatures from the shapes of plumes that arc like loops, and from the stability of certain lanes across many years. The picture remains a measured possibility rather than a settled command. Why this engine matters follows simply. Massive stars control their ends and their gifts to space by how they lose mass. If the engine operates mainly as a steady wind with episodic boosts, then the star can shed enough material to adjust its internal structure, gently, potentially lengthening the time it spends in a quiet late phase and allowing dust to assemble in quantities large enough to seed future clouds. If instead the engine required rare violent events, the environment would look sparse between shocks, which is not what the layered arcs and persistent fans around VY Canis Majoris show. The calm structure supports the steady engine view, lift by cells and waves cooling, and molecule formation, condensation of grains and radiation pressure, guiding the flow, all shaped by rotation and possibly threaded by magnetic influence. Observational tests reinforce the sequence. When near-infrared brightness rises softly, while optical light remains muted dust warming near the condensation zone, is implied rather than a surge in core power. When sub-millimeter lines broaden slightly in sync with those changes, mild shocks are implicated in lifting gas to where it can cool and form molecules. When polarimetric maps show new patches of strong scattering, aligned with earlier surface hotspots, new grains are present in a plume that has just taken hold. The engine therefore leaves linked signatures across time and colour, which is why the narrative can be held without needing a single number to be exact. A soft closing promise completes this section. The engine described here explains how matter starts its journey, but shaping also happens as the flow moves outward, where magnetic guidance, if present, can strengthen or weaken, and where favoured directions persist or fade. The next step is to trace magnetic hints more carefully, to see how loops and threads might gently steer plumes into the asymmetric fans that define the surrounding nebula, and to weigh that guidance against what rotation and surface cells already provide, keeping the picture patient and clear as the story widens. To continue magnetic guidance enters as a quiet possibility that threads through the larger story, and the early takeaway is that even modest magnetic fields can shape where matter flows by easing turbulence along certain paths, and by helping molecules and grains survive long enough to become a wind. A magnetic field is a region where moving charges feel a force, and in a cool, extended atmosphere, those charges include electrons, ions, and charged dust grains that respond gently but persistently to that force. The first hints come from polarization in scattered light and from polarization in matter emission, because magnetic fields can align grains and can imprint a preferred orientation onto the light that leaves dense pockets of gas. Polarization is a preference for light waves to vibrate in one direction, and when maps of that preference span a fan or an arc, they sometimes trace lines that curve like a loop instead of splaying randomly. A small payoff arrives here where polarization lines bend smoothly across a plume. The geometry suggests ordered influence, and not only chaotic motion, which fits the idea that a field threads the outflow. Master emission is naturally amplified microwave light from specific molecules, and in the envelope of VY Canis Majoris, bright mesa spots from molecules such as water and silicon monoxide act like beacons that broadcast the local conditions. Zeeman splitting is magnetic fields, splitting spectral lines and maser lines that show circular or linear polarization patterns, hint at field strength and direction within the clumps that host those masers. Very long baseline interferometry follows those maser spots with exquisite accuracy, so the same clumps that reveal motion can also reveal field structure tying guidance to flow. Another small payoff follows when the preferred orientation of matter polarization lines aligns with the long axis of a plume. The simplest reading is that the field is pulling the flow into a narrow lane, rather than letting turbulence spread it outward. Field geometry matters in a gentle way. Poloidal describes field lines that run from pole to pole, and toroidal describes field lines that wrap around the star like a belt. Real envelopes likely host mixtures, but even a mild tilt toward one geometry can steer material toward an equatorial fan or into broad polar lobes. In VY Canis Majoris, the envelope is not a strict bipolar hourglass, yet several fans share similar lean, and some arcs curve as though their outer edges ride along gently arcing rails. A visual anchor helps imagine very fine iron filings falling through a weak bar magnet's field. The grains do not snap into rigid bars, they drift along faint curves that guide their fall, and the plumes seem to respect similar soft paths. In the near-infrared, where dust close to the condensation zone glows warmly, some features repeat at similar position angles over spans of years, which implies that the launch neighborhood holds a stable orientation. Rotation could cause that on its own, but a magnetic field can stabilize and prolong favored lanes by quenching small eddies and by directing charged particles along field lines, and the quiet endurance of certain fans fits that picture. Ambipolar drift is neutral gas, sliding past ions tied to magnetic fields, and in a cool outflow this drift can slowly transfer the field's order to the bulk material without generating violent heating, which keeps dust formation zones intact. A second visual anchor can rest here. Picture strands of a harp stretched across a dark stage. Fingers pass lightly along the same few strings time after time, and the air between the strings gathers the sound into bands. The star's field and slow rotation play those roles, guiding Plumes into repeated lanes. Observational tests soften speculation into cautious inference. If magnetic guidance matters, then maser polarization angles should correlate with the position angles of Plumes seen in scattered light and in thermal infrared maps, and in several regions they do. If magnetic guidance matters, then arcs from different epochs should share curvature that mirrors a steady set of field lines, and some arcs do curve in family patterns that are hard to ascribe to chance. If magnetic guidance matters, then circular polarization in certain maser transitions should rise with local density in ways predicted by simple models, and measurements often lean that way, though uncertainties in massive physics remain. The payoff here is not a verdict, but a strengthened pathway. Magnetic influence rotation and surface cells can work together in a shared frame, where the field provides rails, rotation sets preferred latitudes, and cells deliver the pulses that launch material down those rails. Why this matters reaches beyond geometry. Magnetic fields can carry waves upward without much heating until they dissipate near the surface, and such waves can deliver extra push at the right altitude to help launch matter without requiring a violent shock. Magnetic fields can suppress turbulence in narrow corridors, letting grains grow to larger sizes before they are shattered, which raises the effectiveness of radiation pressure and raises the survival of grains that later enrich the interstellar medium. Magnetic pressure is the pressure from a magnetic field, and even if it is weaker than gas pressure, it can still bias the shape of the outflow, where gas pressure is falling near the edges of Plumes, turning sharp boundaries into rounded forms that match observed arcs. Another payoff settles in this suite of gentle effects explains how a star can build a richly structured nebula without resorting to rare cataclysms, and it explains why some directions repeat in the record of ejections. Uncertainties remain, and they are handled calmly. Measuring field strength in dusty variable envelopes is difficult because polarization can also arise from scattering geometry, and not only from aligned grains or Zeeman splitting, and matter physics involves saturation and beaming that can mimic some signals. To reduce confusion, observers compare multiple matter species, multiple lines of the same molecule, and multiple wavelengths of continuum polarization, looking for patterns that persist across methods. Where patterns match, confidence rises. Where they differ, models improve by adding subtleties such as changing grain shapes, evolving grain sizes, and variable illumination. The present picture for VY Canis Majoris is therefore measured magnetic guidance likely contributes perhaps modestly but meaningfully in concert with rotation, and with the rise and fall of surface cells. A final visual anchor closes this section. Imagine a slow aurora that never flashes, only drifts its pale curtains shaped by unseen lines, while a steady breeze slowly presses them outward. The plumes of VY Canis Majoris seem to hang on similar unseen threads as they slide into space. The gentle handoff is clear, with magnetic hints set beside rotation and surface dynamics. the narrative can now turn to rotation itself, and to the ways a broad, slowly spinning star naturally builds a symmetry, so that the favoured lanes suggested here become understandable consequences of shape and motion, rather than mysterious exceptions. To continue, rotation enters the scene as a quiet sculptor, and the early takeaway is that even slow spin can tilt an atmosphere this vast into favoured lanes, where outflow gathers, so a symmetry becomes a natural outcome rather than a surprise. Effective gravity is gravity reduced by the outward push from rotation, and on the bulging surface of a red hypergiant, the effective pull is a touch weaker near the equator than near the poles. That difference, though gentle, lowers the pressure needed to lift gas at certain latitudes, and a slight ease in lifting can be the difference between material that falls back and material that glides outward to cool and condense. Oblateness is a slow flattening from pole to pole, and in a cool, extended star the shape does not sharpen like a spinning top but swells broadly. The change is enough to redistribute pressure and temperature without breaking the calm picture drawn so far. A visual anchor helps imagine a paper lantern turning very slowly, so slowly that the eye hardly notices, and yet a faint belt of warmer air gathers around its middle where the curve is broadest. In the same way, the equatorial region of the star becomes a patient runway for outflow. Gravity darkening is the tendency for regions with higher effective gravity to appear slightly hotter and brighter, though in a star with deep convective layers this contrast softens. Still, the combination of shape and temperature can make an equatorial band a friendlier place for molecules to survive and for dust to form. When dust appears closer and more often at those latitudes, radiation pressure gains a better grip, and the outflow thickens into fans whose edges align across repeated ejections. Shear is the change in rotation rate with latitude or depth, and shear stretches the bases of giant convection cells, turning round footprints into ovals that preferentially lean along lines of constant latitude. This stretching matters because a stretched cell tends to persist, and to relaunch material from similar neighbourhoods, which explains why several plumes can share the same broad direction for years. Coriolis effect is the deflection of moving flows caused by rotation, and in this atmosphere it gently bends rising streams, tipping them sideways so that plumes appear at odd angles that repeat, rather than at random angles that cancel. A small payoff settles in here. Rotation need not be fast to produce structure. By slightly easing lift at favoured latitudes, by bending paths, and by stabilising stretched surface cells, rotation explains a stable set of fans without invoking violence. Meridional circulation is slow flow from equator to poles, and back again within a rotating envelope, and such circulation can carry heat and composition in broad loops. Where this circulation brings slightly cooler, denser gas toward the equatorial belt, it further encourages condensation, sharpening the contrast between belt and higher latitudes. Rossby waves are large-scale waves that live in rotating fluids, and on a star they may migrate slowly, altering the timing of favoured launch zones without erasing them. That behaviour fits the observed pattern of families of arcs appearing fading and then reappearing nearby. A second visual anchor can rest here. Think of a lake with a very slow carousel beneath the surface drawing long gentle swirls. Fallen leaves gather in the same tracks night after night, and the plumes of the star gather into similar swirls set by slow spin. Rotation also affects how dust and light meet. If equatorial lanes become thicker, then optical depth along those directions increases, casting soft radial shadows into the outer envelope that match the dim wedges seen cutting across older arcs. Where the equatorial band is slightly cooler, seed clusters of silicate minerals form earlier, and in larger numbers, and more seeds translate into stronger coupling with starlight, which strengthens the push that carries gas along. The result is a feedback that remains calm. A small rotational preference makes more dust at certain latitudes. More dust makes the wind stronger there. The stronger wind keeps the lanes open for the next ejection. Observational hints align with this picture. High-resolution images at near-infrared wavelengths often show bright patches that repeat at similar position angles, consistent with long-lived cells stretched by shear. Thermal maps reveal warm inner dust that outlines fans whose midlines stay steady year after year as expected, if rotation and possibly magnetic guidance set rails that surface dynamics then use. Polarization patterns across arcs show alignments that lean toward a common axis, while the shapes of outer fans suggest a mild equatorial preference rather than a strict bipolar hourglass. Line profiles from molecules that trace motion show a bias towards certain latitudes in their speeds, reinforcing the idea that the flow is not uniform with direction. Another small payoff arrives taken together. These signatures do not demand a rapid rotator. They are exactly what a broad, slowly turning star would leave if rotation were one shaping influence among several. Rotation carries evolutionary consequences that matter beyond geometry. Angular momentum is the measure of spin, and the outflow carries angular momentum away along with mass, so the star slowly spins down as it sheds material. Spinning down changes how convection cells interact and how waves travel, and that change feeds back into the engine described earlier, likely making outflow even more equator-friendly as time passes, because a broader cooler atmosphere supports dust formation closer to the surface. A calm reassurance follows. None of this implies sudden change. Rather, the star adjusts itself with patient steps, altering the distribution of its wind in ways that can be read in the layered arcs already mapped. A further visual anchor can help the mind hold the scene: a grand old tree turning imperceptibly season by season. Prevailing breezes carry leaves along the same 2 or 3 paths down the hill, and each autumn traces those paths again. Rotation and outflow work together in the same repeating way. The role of rotation also clarifies why the nebula is not a perfect sphere, and not a narrow hourglass but a set of overlapping lobes. Equatorial fans carry denser flows. Higher latitudes still launch material but with less efficiency. The result is a collage of arcs that open broadly near the equator and soften toward the poles. When such geometry is deprojected using proper motions and line-of-sight speeds, the three-dimensional picture settles a gently flared equatorial region and a family of inclined slices where repeated plumes have layered their traces. The soft closing promise of this section is that rotation provides the frame upon which chemistry paints its colours. Where the spin eases lifting and guides lens dust seeds and mineral growth, set the texture and the brightness of each fan. The next step is therefore to move inward to the condensation zone and to examine with simple restful language how dust seeds form what they're made of, and why their growth near the star decides how strongly the outflow shines, and how much of that material will one day become part of the wider interstellar medium. To continue chemistry lights the lantern inside the wind, and the early takeaway is that dust seeds form close to the star in orderly steps, then grow into grains that decide how bright the fans appear and how strongly the outflow pushes. Condensation is atoms and molecules sticking to become solids, and in the warm inner envelope of VY Canis Majoris, the first condensates are the most heat-resistant materials. Refractory means hard to vaporize, and refractory oxides form first where the gas cools below their survival threshold. Alumina is aluminum oxide, and tiny clusters of alumina can appear just above the region where the photosphere's glow gives way to a haze of newly born grains. Nucleation is the birth of the very first solid clusters, and nucleation requires supersaturation, which is a slight excess of molecules over what the warm gas can hold. Supersaturation rises behind passing shocks, or within rising surface cells that lift gas and let it cool, so the conditions favouring nucleation repeat along the same lanes where plumes begin. A small payoff lands here. This sequence explains why the earliest light scattered from dust hugs the star along narrow paths rather than forming a uniform ring. As the gas flows outward, alumina seeds become hosts for silicate growth. Silicates are minerals built from silicon and oxygen, often mixed with magnesium and iron, and in an oxygen-rich wind they dominate the dust budget. Growth is the attachment of atoms to a solid surface, and growth rates depend on temperature density and the availability of the right molecules. Silicon monoxide, water, and carbon monoxide mark the chemistry of this region, and their measured strengths tell observers which zones are ready for silicate assembly. Another small payoff follows when near-infrared maps show a warm ridge, and submillimeter spectra show strong silicon monoxide emission in the same place that overlap points to an active condensation front where fresh grains are being made. Grain sizes begin tiny and then separate into two broad families as the wind moves outward. Some grains remain small and scatter visible light efficiently, sharpening the lacework seen near the star. Other grains grow larger and absorb more light than they scatter, which makes them glow in the infrared and strengthens the radiation pressure that propels the wind. Albedo is the fraction of light reflected, and emissivity is the ease with which a surface emits thermal light. Small bright grains keep albedo high, while larger iron-rich grains boost emissivity and deepen the infrared glow. The balance between the two families varies by lane because a slightly cooler plume allows more growth before grains drift beyond the densest part of the flow. A visual anchor helps imagine dew forming on spider silk before dawn, first as tiny sparks that glitter, then as larger beads that shine warmly once the sun rises. The dust around the star behaves like that dew along the quiet filaments of the wind. Mineralogy leaves distinct signs in the spectrum. Amorphous silicate, which lacks crystal order, produces a broad band near 10 micrometers and another near 18 micrometers, and these bands rise in the inner and middle envelope where silicate grains are young and warm. Farther out, where grains have time and warmth enough to rearrange some portion, may anneal into partially crystalline forms. Annealing is slow reordering of atoms within a solid, and it can sharpen parts of the infrared bands and add faint narrow features that ride atop the broader shape. Spinella, magnesium, aluminum oxide, and other minor oxides may contribute at specific wavelengths, especially near 13 micrometers, and these delicate lines give gentle constraints on temperature and composition in narrow lanes of the fans. The payoff is practical. By measuring the shapes and strengths of these features along each plume, observers build a map of grain growth, heating and cooling that doubles as a history of each ejection. Chemistry also governs how light pushes. Radiation pressure couples most strongly to grains whose sizes match the wavelengths of peak stellar light, and as grains grow from sub-micrometer sizes toward a few micrometers, the push strengthens. Momentum sharing is the transfer of motion between grains and gas through collisions and drag, and efficient sharing is why gas rides along with dust rather than stalling behind. Optical depth. The measure of how much light is blocked grows with both density and grain size, so a plume, thickened by vigorous grain growth, can cast a long, soft shadow into the outer envelope, sculpting the dim wedges seen in mid-infrared images. A second visual anchor can rest here. Think of a hand passing before a bedside lamp, not blacking it out, but turning the wall into a gentle gradient of light and shade. The thicker plumes do that to the older arcs in the distance. Grain charge and shape add quiet texture. Ultraviolet and visible photons can knock electrons free, leaving grains slightly charged. Charge affects how grains interact with any magnetic field present, and elongated grains can align with that field, introducing a preferred polarization pattern that helps reveal geometry. Shape also changes how grains scatter and absorb light. Fluffy, porous grains have different scattering behavior than compact, glassy grains, and that difference appears in the ratio of optical to infrared brightness along a plume. Why this chemistry matters reaches beyond appearance. The efficiency of dust production sets the mass loss rate that the star can sustain without sudden violent episodes. If grains form easily and grow steadily, radiation pressure can keep the wind flowing with minimal shocks, and that steadiness matches the layered arcs observed. The mineral mix also decides what the star gives back to space. Oxygen-rich dust carries silicate minerals, alumina, and traces of iron compounds, and those become part of future clouds that will one day birth new stars and new planetary systems. Water can freeze farther out into mantles on grains, where temperatures allow creating icy coatings that alter sticking behavior in cold interstellar places. A third payoff arrives here. The chemistry along a plume therefore tells a future story not only of brightness and shape near the star, but also of what ingredients will be available to the next generation of worlds. Uncertainties remain gentle and tractable. The exact path from alumina seeds to specific silicate minerals depends on cooling rates and on local gas composition, which varies from plume to plume. Some studies hint at pockets with more iron which darken grains and raise their infrared emission. Others hint at more magnesium-rich silicates that scatter light more brightly near the star. These differences, rather than disturbing the narrative, enrich it by explaining why two plumes with similar shapes can show different color balances. The soft close for this section is a simple confirmation. Chemistry near the star determines how easily grains are born, how quickly they grow, how strongly they are pushed, and how brightly they glow. The close coupling between condensation growth and radiation pressure turns the inner envelope into a workshop whose output paints the fans and arcs. With the seeds and minerals now clear, the path leads naturally to the images of the surface itself, where bright patches and shifting cells have left footprints that match the birthplaces of plumes, tying the chemistry of dust to the geography of launch sites in a single restful picture. To continue, the surface of VY Canis Majoris comes into view as a shifting tapestry rather than a smooth globe, and the early takeaway is that high-resolution techniques now glimpse bright patches, dark lanes and subtle asymmetries that connect directly to the birthplaces of plumes. Interferometry is the act of linking many telescopes to create a single sharper eye, and near-infrared interferometric images resolve the stellar disk into mottled structure, where some regions glow warmer while others appear muted and cool. Adaptive optics on the largest ground-based mirrors steady the atmosphere above the observatories and sharpen the view, while space-based platforms avoid atmospheric blur entirely. Together they deliver images and reconstructions that show a face in motion, a face that never freezes into a single pattern. A small payoff arrives here. The brightest patches on the resolved surface often align with the midlines of fans and with the roots of arcs seen farther out, which ties surface geography to the later shape of the nebula. Convection cells rise and sink across this enormous photosphere. A convection cell is a loop of hot rising gas and cool sinking gas, and on a star this large, each loop can span a meaningful fraction of the disk. Where a cell rises, the surface grows warmer and brighter. Where it sinks, the surface cools and dims, building a patchwork whose texture evolves on timescales of months to years. Gravity is gentle at such a swollen radius, so the tops of rising cells carry gas higher than in more compact stars, and that extra lift prepares local regions for dust formation once the gas cools just above the photosphere. The pattern is not random. Elongated footprints appear stretched along lines of latitude by rotational shear, and these elongated regions persist long enough to launch multiple plumes that later form fans in similar directions. A visual anchor helps imagine an orange paper lantern lit from within its silk skin, dappled by slow eddies of warm air that gather in ovals and wander but do not vanish quickly. This stellar face looks like that, alive and patient. Spectroscopy across the disk adds quiet detail. By spreading light into colours and sampling at many points, observers measure slight changes in temperature and in the strengths of molecular bands, finding that the warmer patches show weaker molecular absorption, consistent with raised temperatures, while cooler patches show stronger bands where molecules thrive. Doppler shifts across the surface reveal subtle outward and inward motions tied to the cellular flow, and at times localized outward drifts align with later plume directions, offering a gentle causal trace from surface surge to launched outflow. Another small payoff follows when imaging shows a persistent bright oval near a particular position angle, and later epochs reveal a new arc in that same direction. The simplest reading is that the cell hosted repeated lifts that seeded that arc family. Near the limb where one looks through longer paths of gas, the atmosphere shows extended hazes that rise above the photosphere, and that limb brightening and limb darkening pattern varies with wavelength in ways that map the thickness and temperature of those hazes. Polarimetric imaging near the star records the orientation of scattered light and shows that just above some bright patches the polarization rises, and the angle swings a signal that new grains are forming and redirecting light, which confirms that cell crests are natural launch pads. The role of shocks appears in line profiles that broaden subtly over bright patches, consistent with low Mach number compressions that jolt gas without tearing it apart. Such shocks increase supersaturation and promote the nucleation of dust seeds, closing the circle between surface dynamics and chemistry. The face changes with time in ways that are slow enough to track, yet lively enough to hold attention. Monthly sequences show bright regions that drift, split, and sometimes merge, while darker lanes slide between them like rivers dividing islands. These motions are not frantic. They are deliberate, like weather systems on a global scale, with each system preparing the local sky above it. Rotation introduces a gentle migration of features. A bright oval will appear at one position angle and then slide to the side over several months, all while raising and sinking like a tide as the cell beneath it waxes and wanes. The cadence of these changes matches the slow rhythms in the light curve, and the alignment between peak brightness phases and the appearance of fresh scattering very near the surface supports the view that the face itself is the metronome for mass loss episodes. A second visual anchor can rest here. Think of a simmering sea at sunset seen from far above, where broad glassy plates of water brighten in turn as swells lift them toward the light. The star's face reveals that same procession of glints, each glint a promise of a plume to come. Techniques that sharpen the view also sharpen the story. Closure faces in interferometry detect asymmetry. Even when images are blurred and repeated, detections of non-zero closure phase confirm that the surface is lopsided in illumination. Image reconstructions that respect those closure phases produce stable patches rather than capricious spots, and independent instruments recover similar structures, which reassures that the features are physical and not artifacts. When these reconstructions are compared to contemporaneous maps of the inner envelope at near-infrared wavelengths, bridges emerge, a bright elongated surface patch points into a wedge of warm dust that a little later extends into a broader fan, and after still more time, an arc appears farther out that shares the same position angle. A third small payoff follows this chain from face to near dust to far arc, shows that the geometry of the nebula is at heart a record of what the surface has done. The resolved face also frames the roles of rotation and magnetic influence in a measured way. If a preferred axis exists, bright patches grow more often along it, and fans align with it. If magnetic loops arch above certain regions, polarization near the limb will tilt consistently there, and some fans will trace gentle curves that echo that tilt. The data suggest both patterns without insisting on a single cause, which fits the theme that several quiet forces combine to steer the wind. Just as important are the absences. There is no sign of violent global shocks ripping across the face. Instead, there is endurance and gentle renewal, a portrait of a star managing loss through structured breath rather than through rare convulsions. Why this matters extends beyond the beauty of a resolved surface. A face that can be mapped and followed in time allows models of massive star atmospheres to be tested directly, and those models in turn inform how mass loss should be treated in the life cycles of the most luminous stars. If structures like these are common among red hypergiants, then the universes between such stars and their later fates will often be shaped by similar patient engines, and the dust budgets of galaxies will carry that signature. The soft close of this section is an invitation to read the face as a clock. The motions of patches and the motions of knots in the nebula can be paired so that each outward step of a clump corresponds to a moment on the surface when lifting peaks. The next section gathers those motions into a calendar, turning positions and speeds into ages and assembling a gentle timeline of ejection episodes that quietly explains how the surrounding arcs came to be. To continue motion turns the clumpy envelope into a soft calendar, and the early takeaway is that positions and speeds together become ages, so each knot and arc carries a date that tells when the surface last lifted with enough strength to send matter outward. Proper motion is the change of position on the sky, with time and repeated images taken years apart reveal that bright knots drift away from the star at steady rates that vary from lane to lane. Line of sight speed is the component of motion toward or away from the observer, and spectra of molecules, such as carbon monoxide, silicon monoxide, sulfur monoxide, and water convert tiny shifts in color into those speeds. When proper motions and line-of-sight speeds are measured for the same clump, the two combine into a three-dimensional velocity, and with distance known that velocity becomes a ruler and a clock. A small payoff arrives here. Divide a clump's present separation by its speed, and a launch age appears, often measured in decades for inner arcs and in centuries for the more distant shells, revealing that the star's breath has been organized into episodes that repeat but do not rush. Homologous expansion is a pattern in which features farther out move faster by just enough to keep the whole shape scaled with time, and several fans around VY Canis Majoris behave this way, which means the fans preserve their profiles while they expand like a painted design stretched on a slowly inflating lantern. This behavior matters because it assures that the present snapshot can be rewound reliably. Tracing the motion backward gathers each fan toward a compact patch near the star at a specific time, in the recent past linking fans to surface neighborhoods with quiet confidence. A visual anchor helps imagine a group of paper lanterns drifting from a festival, the farther ones moving just a little quicker, so that the pattern of their positions keeps its shape while it slides away. The envelope of the star follows that same law of gentle scaling. Spectroscopic maps add subtlety by showing where the flow is slightly tilted relative to the plane of the sky. If the blue shifted side of a fan is brighter in certain lines, while the red shifted side is brighter in others, then the fan is inclined and one edge is tipped toward the observer. Inclination is the tilt of a structure relative to the line of sight, and measuring inclinations across many fans turns a flat picture into a layered volume, assigning each arc to a near or far side with soft certainty. Another small payoff follows when the inclination of a fan matches the orientation of polarization patterns in scattered light. Two independent methods agree, and agreement reduces ambiguity even when dust density changes across the field. The calendar that emerges is calm rather than crowded. Inner knots with ages of a handful of years trace the freshest plumes, often aligned with bright surface patches seen in recent interferometric images. Middle arcs with ages of a few decades record families of events that launched from similar latitudes and position angles, weaving overlapping curves that open like a hand. Outer arcs with ages of a century or more remember a time when the star favoured slightly different lanes, suggesting that the long-lived convection pattern and the gentle rotational frame have shifted only slowly. The pattern of intervals is instructive. The gap between major ejections along a given lane is long enough for grains to grow drift and cool into rounded clouds before the next plume follows, which explains why arcs retain identity rather than merging into a featureless fog. At the same time, the gaps are short enough that several siblings are often visible, within a single fan offering a sequence that models can test. A second visual anchor can rest here. Picture the rings of a tree trunk not as perfect circles, but as arcs that grew thicker where a given season favoured one side. Reading the envelope of VY Canis Majoris feels like reading such rings with wider and thinner bands, marking years of stronger or weaker lift. Linking motion to surface timing completes the clock. When light curves show a period of gentle brightening in the infrared, followed by a soft dimming, and when near-infrared imaging soon after reveals a new patch of strong scattering near the condensation zone, a seed plume is suspected. If within a few years a knot appears along the same position angle and begins its outward drift, the sequence of photometry, inner imaging and motion becomes a chain of evidence. A surface cell rose dust formation strengthened, and a plume launched. By repeating this matching across several episodes, observers build a timeline that pairs specific surface neighborhoods with families of arcs, strengthening the story that the face is the metronome and the nebula is the record. Uncertainties exist and are handled gently. Dust can hide the true center of light, biasing measured separations. Observers correct by using multiple wavelengths and by tracking features relative to one another as well as relative to the star. Projection effect can make speeds appear smaller or larger, depending on inclination. Models account for this by fitting the full three-dimensional flow to both the proper motions and the line of sight speed simultaneously. Some lines form in gas that is not coupled perfectly to dust, which can shift the apparent speed slightly. Comparisons among several molecules with different formation zones help control this. After such care, the remaining uncertainties are small compared to the broad rhythm that matters most. Another small payoff settles in. Even with cautious error bars, the ages align well enough to reveal clusters of events around certain decades and quiet periods in between, a pattern that echoes the endurance of long-lived surface cells and the slow drift imposed by rotation. The calendar carries consequences for mass loss budgets. Knowing the ages and speeds allows masses inferred from thermal emission and scattered light to be converted into rates for each episode and into averages over longer spans. These rates confirm that repeated moderately strong ejections can account for a large share of the total mass lost in the recent past without invoking rare violent events. That conclusion fits the smoothness of the observed expansion, the absence of strong shocks in most line profiles, and the continuity of grain growth signatures across distance. The wider importance touches how massive stars edit themselves before their final acts. The timeline shows that a red hypergiant can restructure its outer layers through sustained structured breathing, steadily lowering envelope mass, seeding the immediate sky with dust and setting conditions for whatever quiet turn comes next. A final visual anchor closes this section. Imagine a music box that plays a slow theme, each note a plume, each bar a fan of arcs, and as the melody repeats with slight variations, the dancer in the glass dome turns with patient grace. The envelope of VY Canis Majoris is that music in space and its motions are the timed steps. With the dates read and the rhythm understood, the narrative can turn to the life stage of the star itself, and to the measured futures that follow from this calm but persistent release of matter, framing what lies ahead without alarm. To continue, the life stage of VY Canis Majoris unfolds as a long-measured turn through late evolution, and the early takeaway is that steady mass loss now governs what happens next, setting both the timescale and the path in a way that is calm rather than catastrophic. A red hypergiant is a massive star that has expanded and cooled at the surface, while its core continues to fuse heavier elements in nested shells, and in such stars the outer envelope becomes loose enough that even gentle engines can carry matter away. The deep interior remains hidden, but the envelope tells its story clearly repeated. Structured outflow means the star is actively editing itself, peeling mass from the outside to keep the inside on a stable course for longer than a single violent event would allow. A small payoff arrives here. The layered arcs and persistent fans are not just scenery. They are the mechanism by which the star controls its own future, by lowering envelope weight, cooling the outer layers, and making the next steps less abrupt. As mass leaves the balance between gravity and pressure in the envelope shifts. Lower envelope mass reduces the pressure that presses down on the burning shells, and that can slow or soften changes that would otherwise trigger large excursions in temperature and radius. Episodes of enhanced mass loss followed by calmer intervals allow the star to find new equilibrium states rather than swing wildly, and the observed semi-regular light changes fit this view of patient adjustment. The result is a sequence of stages that move the star not on a straight line but through a set of neighbouring rooms in the same house. Red hypergiant today, perhaps a somewhat warmer, slightly smaller supergiant tomorrow, with the door between those rooms opened and closed by how the wind removes mass, and by how the inner energy output varies within familiar bounds. A visual anchor helps imagine a great bellows breathing slowly beside a hearth. Each outward breath scatters ash and lightens the bellows, making the next breath easier and quieter. The star performs that same gentling as it trims its envelope. The possible futures are framed by mass rotation and outflow history. If the envelope remains heavy enough for a long time, the star may maintain a red hypergiant face, while continuing to shed mass in structured plumes, building a more extended cooler nebula, with arcs that grow broader and softer. If mass loss proceeds to the point where the envelope thins appreciably, the surface layers may contract and warm, leading to a transition toward a yellow or orange supergiant state, where dust formation becomes less efficient close in, and where outflow becomes more purely gaseous until new balance is found. If the internal burning advances while mass loss continues, the core can approach the conditions needed for a final collapse, but even then, the observed environment argues for a gentle lead-up rather than a sudden upheaval. Another small payoff follows whatever the exact path the existing record shows, that patient release can dominate for decades to centuries, and that timescale allows astronomers to witness meaningful change without alarm. The endgame for massive stars is often a supernova, but the envelope state at the moment of collapse shapes how that supernova looks. A dense, clumpy circumstellar medium can turn the outer stages of an explosion into a luminous conversation between fast ejecta and slower dusty shells lifting brightness and carving structure into the emergent light. A thinner, more uniform envelope can yield a more classic plateau, or a different light curve with less immediate interaction. The arcs and fans around VY Canis Majoris therefore serve as a forecast of what kind of surroundings any future outburst would encounter, and the forecast is not one of disaster, but of information. The geometry, densities and distances mapped today would help interpret the light of tomorrow. This matters because such nearby richly structured laboratories teach how to read distant, unresolved events, where light curves and spectra are the only guides to the history of the star that exploded. The feedback to galaxies flows through this same channel. Dust made near the star leaves in the wind, and later in any terminal event, and that dust carries minerals and ices into the interstellar medium. In that sense, VY Canis Majoris already contributes today before any final act. The arcs visible now are the star's present gift to its surroundings. A second visual anchor can rest. Here think of a hillside in late autumn, where leaves drift in patterned lanes that feed the soil long before winter arrives. The star's outflow is that autumn, and the soil is the space between stars enriched by the slow fall. The timescale for significant change is a comfort. The envelope expands at speeds that measure in tens of kilometers each second, which sounds swift, but translates at the scales involved into years and decades for even inner structures to move meaningfully across the sky. Surface patches evolve on monthly to yearly timescales. Chemistry near the condensation zone responds over days to weeks. These tempos are human-friendly for observation and thought, and they mean that the narrative can be updated through careful monitoring rather than rewritten in a rush. A third small payoff settles in by continuing to pair imaging, polarimetry, spectroscopy, and radio mapping. The next increments of change will clarify which future the star is choosing, and that knowledge will arrive as a sequence of gentle corrections, not as a shock. Rotation and magnetic guidance remain in the frame as quiet partners to mass loss. If rotation continues to favour an equatorial band, the long-term shape of the nebula will become more flared with repeated fans building a skirt of dust that thickens at mid-latitudes. If magnetic influence persists, some lanes may remain surprisingly clean and direct, preserving corridors through which later ejections or even later shocks might travel with minimal mixing. In either case, the guiding forces act to preserve memory, which is why the nebula looks legible now and will likely stay legible as it grows. The calm conclusion of this section is that VY Canis Majoris stands in a mature, mass-loss-dominated phase, where the most relevant processes are steady and observable. The star breathes structured winds that shape its near space and regulate its progress, spreading dust that will join the wider medium and preparing an environment that will one day record the last transition with clarity. The narrative does not require a single dramatic turn to be meaningful. The meaning already resides in the cadence of arcs and the chemistry of grains. With that assurance in place, the path forward is to gather the lessons together why this star matters, how its patient engine illuminates the lives of massive stars, and what its layered sky teaches about the quiet ways galaxies are built, grain by grain. To continue, VY Canis Majoris matters because it gathers many quiet truths into one readable sky, and the early takeaway is that this single star, by shedding mass in structured plumes, and by painting its own near space with dust, teaches how the largest stars breathe, how galaxies receive their grains, and how patient observation turns complexity into calm understanding. The first lesson is about engines. Here, mass loss is not an accident or a single dramatic event. It is a sustained cooperation between convection waves, shocks, cooling, chemistry, grain growth, radiation, pressure, slow rotation, and likely magnetic guidance. Because every part of that sequence leaves a signature in light. The star acts as a classroom where ideas about how winds start and how they are shaped can be checked in detail. A small payoff arrives here when the same plume shows a warm ridge in near-infrared images, a scattering lane in visible images, a line of moving molecules in sub-millimeter maps, and a set of polarized patterns that curve gently the chain from surface lift to guided flow, stands not as theory but as a set of matched footprints. The second lesson is about structure and memory. The arcs and knots are not random flourishes. They are preserved pages from earlier chapters, with dates assigned by motion and depth, assigned by colour, and by reading those pages the pace and style of the star's breathing are recovered. The calendar that emerges is steady enough to reassure new plumes arrive, often enough to build fans with siblings, yet not so often that older arcs are erased. The geometry affirms a world without rush, and that steadiness allows models to be tuned in real time, with each season of new images becoming a new test. The third lesson concerns chemistry that travels. The grains formed near the star are the very grains that later become the fine dust in clouds between the stars. Their mineral mix, their sizes, and their charge states now can be mapped, where they are forged, not only inferred after they have wandered the wider galaxy. A second visual anchor helps imagine a workshop with its doors open to the night, where one can walk from the bench to the road and then to the field, following the same crafted object through each space. The envelope of VY Canis Majoris offers that walk for dust from birth near the photosphere to the soft drift across arcs, and out to the cool fans that meet the interstellar medium. The fourth lesson is about measurement itself. Techniques that may seem abstract become tangible here. Polarimetry stops being a word and becomes a compass that draws the tilt of surfaces. Interferometry stops being a diagram and becomes a set of bright and dark patches that line up with later plumes. Spectroscopy stops being a rainbow and becomes a speedometer that turns colour into motion. Very long baseline radio measurements stop being a technical marvel and become a simple way to place the whole portrait at a reliable distance. The payoff is practical and kind. The same instruments and methods used on this star become easier to trust when they are applied to stars that cannot be resolved so well, and the knowledge expands outward with confidence. The fifth lesson reaches to evolution and to fate. A massive star does not hold still while the deep interior changes. Instead, it edits the envelope, lightening it and cooling it through a cadence of ejections. That editing slows and softens later steps and sets the stage for whatever final change will one day arrive. There is no need for alarm in that understanding. The tempos involved are long, the structures are legible, and the record of the past century is a guide to the likely near future. A third small payoff settles in knowing the mass loss rate. The geometry and the densities of the surrounding arcs allows one to predict how any later surge of energy will interact with the nearby medium, turning a distant headline into a solvable page of physics rather than into a mystery. The sixth lesson is about galaxies. Dust created by stars like this one shapes how starlight travels through spiral arms, how clouds cool and collapse into new stars, and how planetary materials begin. By tracing the dust to its point of origin, one sees that the galaxy's dim golden fog is not a uniform smear, but a mosaic built from the patient gifts of many such winds. VY Canis Majoris thus stands not only as a singular spectacle, but also as a representative of a population whose combined influence is quiet and large. The seventh lesson finally is aesthetic and humane. A complex system can be made gentle if approached with time, with many windows, and with a willingness to let patterns reveal themselves rather than be forced. A final visual anchor holds the mind in place, a winter field under a low sun where breath rises in slow veils and glints in pale halos, where footprints keep a soft record of where one has walked, and where the horizon does not insist on urgency. The star's world feels like that field, vast and calm, structured yet forgiving. Why this star matters then is both precise and broad. It is a living proof that late stages of massive stars can be governed by structured patience. It is a bridge between the physics of surfaces and the chemistry of grains, and between local weather on a star and the wide climate of a galaxy. It is a guidebook for reading light where distance makes detail scarce. It is a promise that careful watching makes the unknown familiar. The gentle conclusion is that the story of VY Canis Majoris is already a complete lesson, even as it continues. A listener who holds the image of a slow, luminous lantern, building its own sky, has everything needed to understand. What remains is to let the breathing settle and to rest in the cadence which prepares the way for the quiet wind down that follows where the gathered images are laid out in softer light, and the mind is invited to release its grip on facts while keeping their shape. Now the lantern of VY Canis Majoris glows in a quieter room of the mind, and the gathered images settle like soft dust on evening shelves. A red world of patient breath, a garden of arcs and fans, a face of shifting ovals, and a sky of gentle rails have all become familiar not as noise but as a calm pattern that holds together. The slow rhythms of brightness become a heartbeat. The plumes become steady exhalations. The layered nebula becomes a library of pages turned without hurry. Each idea has taken its place, and each place feels smooth under thought, as if the edges have been rounded by time. To begin the rest, let the scale draw closer and grow smaller until it fits within a quiet bowl of attention. Let the bright patches on the surface dim to warm embers. Let the arcs lean back into a soft haze, their dates and distances folded away like a map closed after a gentle walk. In this softer light the star continues its measured work, and that steadiness passes into the listener as an even breath in and out, a tide without urgency. Picture a winter field where the air is still and the horizon is kind. The breath that leaves the mouth rises, thins, and disappears. The same cadence repeats and becomes easy to follow, and the body takes the cue to release weight into the bed and let the eyes grow heavy. Thought untangles and finds the single thread of a lantern in a mist, a patient glow behind drifting veils, a known path that needs no decision. The mind sets the story down gently beside the pillow. Nothing is unfinished. The lessons hold without being held. The room and the star share a single quiet, and the long arc of the story tapers into a line of rest. The line shortens, softens, and becomes sleep.